Good morning and welcome back today. I think yesterday was the hard work. You know, building the foundations is always a bit hard. You have to dig deeply into the conceptual world. But today we are going to harvest. We're going to show you how you can simplify systems by using the appropriate simplification strategies. Let me start out by two quotes on the topic. The first one says you should start with a small and simple system if you even want to build a big system. And I think this is not only about complexity, but also about system evolution. That means when we tend to build something large, we should try to start out, have a big plan, but start out small, get feedback from the environment, and then go on to build later and later, the later steps. If you have too large a project at the very beginning, the probability that you will fail due to the complexity is very high. And there are a number of examples showing this. For example, the air traffic control system in the US, where they spent a few billions of dollars and then they gave up because they couldn't make it. The second one is a quote you already know. And I like this quote very much. It's from a Nobel Prize winning computer scientist and economic scientist, Herbert Simon from CMU. And he says, if we don't have hierarchies, multi-level hierarchies to frame our models, to put the models in a hierarchic framework, then we will not succeed in understanding a complex system. It may even escape our observation that there is a system relationship among the parts. So let me start out now with the real thing and look into simplification strategies. If we have a model that is larger than our limits of the conceptual apparatus of our mind, if we cannot put the model into, so to speak, a monolithic system in our mind, we have to partition the model into parts, into smaller parts. And I think there are a number of techniques to simplify a large model. There is the divide and conquer, abstraction, and new conceptualization. And these are three related techniques, but they are fundamentally different. By far the most important of the three techniques is the divide and conquer techniques. But before I go into discussing this technique, let me talk a few words about the limits of human cognition. What can we really handle in our brain? And I'm sure most of you know Sudoku, a Sudoku game. And that's a good game because it shows you just at the edge of what can be done and what is easy and what is very difficult, what can be done. It shows that if there are more than three relations to consider at the same time, that's about the limit of our rational cognition. Some people can handle four, but only very few people can handle four. And this is according to the theory of Halford, the relational complexity theory. He says that three relations are about what the adult human can operate with. If he's a young person, a child, it's two relations. And there are a lot of experiments supporting this. The other limit is the capacity of our short-term memory. And there is this seminal paper by Miller. It says that we can store 5 to 7 chunks of information at the same time in short-term memory. Now, by chunks of information, we mean we put something together which can be handled as a single concept. We also could say we can store 5 to 7 concepts in our memory at the same time. If it goes beyond that, some people can do it, but most people have difficulties. Just think of a telephone number. If your telephone number has more than 7 digits, it's very difficult to recall it immediately, or if something has more than 7 alternatives, it's getting difficult at the limit of our human cognition. So if things get too difficult, too complex in that sense, or too large, we have to partition the whole into parts, and we call the parts components, okay? And the idea here is to have a large monolithic model, and we partition it into a number of smaller models such that the models can be handled. And then we try to arrive at sub-solution of every one of the smaller models, and then we combine the sub-solution to arrive at the combined solution. And this technique of divide and conquer is by far the most important technique of simplification. And in the literature, it has different names. For example, modular design, separating of concerns, segmentation in temporal domain. They're all basically using this technique of divide and conquer, putting a large monolithic system into many smaller subsystems that you hopefully can understand. Now, before we go more into detail in this technique, let's look at what we mean by a component. Because we say the whole is partitioned into components, and for us, the component is a subsystem of a large computer system that provides a specified service across a set of well-specified interfaces. And we restrict our view here and say these are message interfaces. That means we consider a component as a hardware-software unit. We need software that is executed on hardware, on the platform of the hardware, and the platform can be used by one component, then we call it a standalone component, or if the platform is shared by many software components, then we talk about a shared component. But according to what we have talked about yesterday about the holonic principle, it would be a very good idea if the components that use the same hardware platform, that operate on the same shared components, don't interact in unforeseen ways with each other. I mean, there shouldn't be any interaction which is uncontrolled at the level of the given design. Now, let us look a little bit at the power of this divide and conquer technique. And let's take a simple, very simple case. We have one monolithic system, and we use now the cyclometric number, which we have introduced yesterday, as a measure of object complexity, and say that there are 16 decision variables in this big component, in this large component. And we partition it in two small components, into independent small components, where each one of them is handling 8 of the decision variables. Okay? Now, what is, if we take McCabe's complexity, what is the simplicity or the complexity measure that we have achieved by this partitioning? And that's quite amazing. It was amazing to me when I did this example. If we have the one large component with the 16 variables, we have 65,000 different paths through this component. And if we have the 8 decision variable components, we only have 512 cases to distinguish, 2 times 256. That means the complexity reduction based on this McCabe metric, where you can discuss if it's a good or bad metric, but it's a reasonable metric, I think. There's hardly any better one I would know so offhand, would mean that we have reduced the complexity by 99%. 99% of the complexity of the big system has disappeared, and we only have 1% left in the smaller system. And you see the power of this divide and conquer technique. This is the reason why this divide and conquer technique is so dominant and so important in the handling of complexity of large systems. Are there any questions to this? I think you really should grasp this, because this is an important insight you should get at this moment. Martin.
The natural follow-up would be the dependence or independence between the two parts.
I'm coming to this. Thank you very much. That's just the topic of my next slide. So what is the critical issue in the divide and conquer technique? Well, the critical issue of the divide and conquer technique is that there are no interactions. If the two subsystems can be found that don't interact directly, as we have done it yesterday, then we have the full advantage of this complexity reduction achieved. But if there is an interaction, there are problems, and I'm going to talk about this in a minute. yesterday we introduced the notion of a formal hierarchy, if you can remember. And the formal hierarchy is a hierarchy where there are no interactions among the parts. The interactions are only related to the whole. So a formal hierarchy, if you can find a structure, a solution structure for our problem which can be mapped into a formal hierarchy, then we have an ideal structure for the simplification and we can take full benefit of this reduction in complexity. Now, if this is not the case, if there are some interactions, then we have to distinguish three cases, or basically two extra cases, altogether three cases. The first one is we have the formal hierarchy. We said this is excellent because the results are resultant. We have no whatsoever side effect and divide and conquer will work, basically. We talked about this yesterday. If we have a holonic hierarchy, then the interactions only occur within a holon and not outside the holon. And then we still have a good solution, but a solution when can bring up emergence. And here we must be careful that it's not as excellent as the left one, but it can happen emergence, particularly if we have loops in our design. And if we have an unrestricted hierarchy, that means we have no holonic hierarchy, we have an unrestricted hierarchy, and we have these red interactions to the outside, either to other holons or to the external world, then of course this is not so good a situation because we don't know what will happen. Our abstraction of the holon at the top is limited and falls apart. That means this system here leads to a system which has an unstructured behavior. So we should definitely try to go here or here, but should be very careful in this one. Now, but there are situations where we cannot do other because there is no way to find a solution that is not having some elements of an unrestricted hierarchy. And in this case, we have to be very careful that these interactions that go from the holon to the outside can be seen and can be monitored. That at least we know what's happening outside our main area of abstraction, which is the top of the hierarchy. Any questions to this? So I think what this means is, on the other side, that if we have protocols here, communication protocols, we said a component interacts with environment by the exchange of messages only. And the question is now, what kind of message protocol should we use? And we definitely should use multicast protocols, not point-to-point protocols. Why multicast protocols? Because if this component is, and this holon, or it's not really a holon, if this component or subsystem interacts with another subsystem, we want to be able to observe this interaction via an independent monitor. Somebody is outside and sees it. That means we have at least two recipients of a message going along the red line. One going to the intended receiver and another one going to the monitor. So we need protocols that are multicast. On the other side, I would like to have protocols that are unidirectional and not bidirectional. Why? Because if the monitor, for example, fails, we don't want the system to be affected. That means there shouldn't be any probe effect. If the monitor doesn't work properly, the system should still work as planned. That means we need protocols where the degree of dependence is asymmetrical. That means the sender is not dependent on the action of the receiver. That means the sender sends a message out just like the broadcast of the radio. The radio station doesn't care if you turn the radio on or off. You can listen or not. And this is exactly the idea of these multicast protocols that we should use in this case, which have a unidirectional flow of control, and it shouldn't be, for example, in TCP/IP or many of the protocols that are used for file sharing or for information sharing, they are bidirectional protocols. You have message sent from A to B and the response message sent from B to A. That means you have a dependence of the sender on the operation of the receiver. And we really want to avoid this. We want to avoid any kind of what is called in the literature as a probe effect. By looking at the messages, we do not want to change the behavior of the system. The system should be just working the same way if you look at it or not look at it. This means this is a restriction on the protocol design. Any question to that?
Have you considered applying these hierarchies both on the physical side and the cyber side, and sort of how in physical world you have big physical components and have sub-components, and you have, I guess, this type of hierarchy reasoning, and you have the same on the cyber side?
Well, we are mainly, well, the physical side normally is given to you. You have a physical process, and you know, take the example we had yesterday on the rolling mill. You cannot fiddle around a lot with the rolling mill. So it mainly relates how we structure our cyber side models. Okay? So it relates mainly to cyber side. But of course, if you would have a chance to design the physical side as well, it would be very, very well indeed if you can bring these ideas down to the physical side as well. But in many cases, you can't.
We had the previous talks looking at co-design and designing the physical and the cyber side.
Yes, I mean, if you can do it, that's perfect. But as I said, in a rolling mill, you can not do very much about it. It's very limited. So let's look how we can partition a large model into a number of smaller subsystems that can be developed more or less independently and then combined to form the overall solution. And of course, coming back to this slide, the best way would be if we could achieve something like a formal hierarchy. So this should be our goal. This one, the holonic hierarchy, is still okay, but we should try to limit these unstructured, unrestricted hierarchies as far as possible. Okay, wait a minute, let me get. So we talk about three kinds of partitioning. I have to get the right slide again. Well, if you partition a large model, there are three different techniques of partitioning. There's one, partitioning in space. This is sometimes in the literature referred to horizontal partitioning. You just take one, the other one, separate from the other. Segmentation in time, that we say we have this model doing at that time, a next model doing it the next time, the next one at the next time. We call this segmentation. This is partitioning in time. Sometimes it's called step-by-step analysis. We go one step, go the next step, go the next step. And the third one is a kind of abstraction. But this is not the full abstraction, because the abstraction has two aspects, abstraction proper and emergence, and we exclude emergence here. And this is called vertical partitioning. Now, any separation of concern that leads to a formal hierarchy, to a full separation of the two components, of course, is the most successful one, because we can reap the benefit of partitioning to the fullest. So let's go first in the most important technique, and that's horizontal partitioning. Partitioning in space. There are a number of components and a number of techniques available how we can partition a large system in space. And the first one probably is the most important one. Given a system where you have a number of different essential requirements. Now, we could talk a lot about essential requirements. I mean, normally a system is designed to provide a certain service, a purpose in the environment. And out of this purpose, there are derived some essential requirements, which a system definitely must provide in order to reach the purpose. And the first horizontal partitioning rule says, for every essential requirement, we should design an independent component. By independent component, actually it would be best if it would be an independent standalone component, not a shared component, although this is not doable in most cases. Why do we like to put every essential requirement into an independent top-level component of a hierarchy? So we are now building the top-level components of our hierarchy. We have the big system, and now we look at the first level of decomposition, at the first micro level, and we say for every functional requirement that is essential, we must build an independent component in the implementation. Why is this so important? Well, if there's a one-to-one relationship between an essential requirement, an essential function, and the corresponding implementation, then let's go from the bottom to the top. Then diagnosis of failure is very easy. If the function is not here, we know the component has failed. We don't have to look along the system, who could be responsible for the failure, because we have assigned every function to a standalone component. If the function doesn't work, the component must be working. So failure diagnosis is very easy. The second one is simple, that we can test and install the essential functions independently of each other. We can say this is an essential function and this is another essential function, and we can test them independent, we can install them independent. We don't have any side effects from other essential functions if they are cleanly separated. Now, normally they cannot be cleanly separated totally. Another big advantage, and this is particularly for a large project, that we can split the design work very cleanly. We can say this essential function is done by group A, the other essential function is done by group B, the third one by group C, and these functions are independent of each other. There's no communication overhead between these groups because everybody has his own work to do, a clear assignment of job, no interaction of communication, and this is of course the very best way to implement a large system if you can split the tasks that have to be done into independent component or independent subsystems, where every group has its own independent subsystem and doesn't have to depend on the other subsystems or the other groups. Then evolution of the functionality. That's a very important point. Every successful system will change the environment. And this changed environment will have an effect on the system itself again. So every successful system will evolve over time, will change over time. And this evolution should be already part of the design thinking, design process, that we say if every function is essential functions independent of the other, then every function can evolve without any changes to other independent functions. We have an idea path for evolution. If the essential functions are intertwined and one is changing, then it might be that other ones, the resource, for example, if I want to put a new hardware or have available a new hardware because I have a more powerful hardware available, and I put it into service for this function, then it doesn't have to be modified to the other functions and so on. And evolution will happen. Only unsuccessful systems don't evolve. Only those systems that don't impact the environment, they stay as they are. But every successful system will evolve, and we have to plan for the evolution. And of course, then the final one is at the top, that the implementation of the essential function is simplified if you don't have to consider interactions with other example functions during the implementation work. Any question to that?
It was more of a general question. Do you see like a component-based architecture as a term in the industry?
Well, this would be a component-based architecture, yes. Yes.
But do you think it's established today in the industry?
No, it is not.
Not yet.
Not yet. I can give you reasons why. But so the next one is normal processing from safety assurance. Let me go to this slide. Let's take a top-level architecture of a drive, of any safety-critical system, and as an example could be a drive-by-wire system. Okay? Now, let's assume we are on level 2 of automation. On level 2 automation, I only need a primary component who does what it's supposed to do. That means it calculates the steering angle and the acceleration value for the car, or braking, which is a negative acceleration. So we only have a primary component. But this is not a safety critical, well, it's a safety critical system, but it relies on the human to do error detection and error handling. And that's why When you have such a car, it says you always have to monitor the road, you always have to keep the hands on the steering wheel, and in case something happens which you don't expect, take control. So the human is responsible for error detection, and the human is responsible for error handling, okay? Now if you go to a next level of automation, where we do not want the human to be that heavily involved, then we need 4 components. So instead of 1 component, we need 4. Why do we need 4? I need first my primary component. That's the one I had before. Then I need the second one to provide the reference for the output values of the primary component. We call it an envelope. That means the second component should be completely independent. It should have its own sensors, its own hardware, its own software, and should calculate an interval for my actuator values. It says the steering angle should only be in this range and the acceleration should only be in this range. Now, we need a third component, the decision component, to decide if the primary component is meeting the constraints provided by the envelope. Okay? And this is what I call a decision component. And then, in case this is not given, that means that the primary component and the envelope component disagree. We don't know who is in error. It could be the primary component or it could be the reference. We only know that there is a disagreement, but we don't know who is in disagreement. But in any case, we would then go to a safe state, which is implemented by a shutdown component. The shutdown component in our case would bring the car to a safe position on the side of the road. So that's the overall architecture. So we have 4 components. They should be completely independent. They should be completely independent to have any correlated causes of failures in the components. So what we are saying here, they should have their own sensors, they should have their own hardware, they should have their own software, and they should be really independent of each other. But, for example, in a drive-by-wire application, the software of the primary component and of the secondary component, also of the shutdown component, will hundreds of thousands or millions of lines of code with all the pattern recognition and sensor fusion and trajectory planning and what there is. And we mentioned yesterday, if you recall, that we say if something has more than 10,000 lines of code, there are hidden design errors in it. We cannot test. Furthermore, this component operates on very powerful hardware, on sometimes graphic processing unit, GPU hardware, specially designed. NVIDIA has a lot of chips for this purpose. And there is the possibility that a single event upset. Do you know what a single event upset is? Somebody knows what a single event upset is?
Bit flip.
A bit flip, yeah. And what is the cause of a single event upset?
Could be radiations or
Radiation, for example, cosmic radiation. For example, if you look at a bit flip, there's some research that's been done on the effect of a bit flip in machine learning. And they say if you have a machine learning program which is used in automotive driving, and in the classification layer of a deep neural network, you have a bit flip caused by a single event upset, which you cannot avoid, then this causes a truck to be changed to a bird. Instead of seeing a truck, you see a bird. And that's quite a big difference when you do driving, if you have a bird ahead of you or if you have a truck ahead of you. And so we see that we cannot avoid it. That, I mean, in these complex software systems, which are part of the, which are part of the primary components, there we have the possibility of transient software faults. I mean, Heisenbugs in the software, and transient hardware faults. That means single event upsets. So we definitely cannot trust these systems. So, of course, the same happens to this one. And, the same happens to this one, and the same happens to this one. So we do have here complex software, and I phrase it, complex software on unreliable hardware. So we cannot trust it. And as I said, if we are very careful in designing, in testing and so on, we might come up to the 10 to the minus 4 10 to the minus 5 failure rate per hour, but definitely way from the 10 to the minus 9, which we would like to have in a safety critical system. So we need a fourth component, a decision component. The decision component, that's something which is very important. It has to be simple, and it has to work on fault-tolerant hardware, that there will not be no bit flips. Or the bit flips will be masked by the fault tolerance mechanism in the hardware. And of course, this is an expensive piece of hardware and a very well-tested piece of software. It must be simple and it must be fault-tolerant. And only then, if we can compare these two by such a dependable piece of equipment, and then go down to the shutdown route in case there's a discrepancy, then we can make sure that any single fault will be handled. Because we assume this one is free of design faults because it is simple and it can be tested exhaustively. And of course, this one will have design fault, this one and this one. And we need to mitigate this by this decision component. So this is the reason why I would propose that this relates not only to automotive system, to any safety critical system, that this would be a good top-level architecture for such a system. Any questions to this? Yes?
How are such shutdown components designed? Because, for example, in a vehicle, if you drive in a tunnel and you have a failure and you said, like, yeah, I need to drive into a safe state, that safe state can be several kilometers away from me, and I still need a high functionality in the vehicle in order to reach that safe state.
Well, you're perfectly right. This is why the shutdown component will sometimes have many elements of the primary components in it.
Okay.
But it has its own sensors, its own software, its own hardware. Still, it's separately tested so that the probability of correlated faults in the primary component, in the shutdown component, are really minimized.
But for a vehicle, for example, how is that? So is there a horizon given? So how far a vehicle still has to be able to drive, let's say, in case of a fault?
Well, normally, no. I mean, normally you would try to go, and this is a very concrete question, go to the next possible stop, which is safe. And I think that the shutdown component should have the full functionality of the primary component. That it even could go for, I don't know, for hundreds of kilometers, but you don't do it because you don't have any error detection anymore in the system. There's another question here in this picture. We have discussed this with automotive companies a lot, and they don't like the idea that you have separate sensors on every one of these subsystems because they say sensors are expensive, and why can't we share the sensors? And if we can share the sensors, then we can save sensors, and the whole thing gets economically. But it's a design decision. But if you share sensors, you have again a common mode failure possibility. If a single sensor that is used by component P, S, and the shutdown component fails, then it will affect all three of them. And so you should not do it. But of course, if economics dictate it and people think they can live with it, I'm just giving you what conceptually should be the right way to do it. I cannot go into economical decisions not to do it, but I think at the end of the day, you should go it this way. Any further questions?
On the secondary component, you have the envelope. Is that, what do you mean by that? Is it like a different system of component architecture in that?
The only thing which the output of this envelope is, for example, if you take a drive-by-wire application, and I wanted to refer to that, you have two outputs of the primary component to the actuators. You have a steering angle and acceleration or deceleration value. I mean, braking or putting more power to the engine. And these are the outputs. How he calculates these two, and it must, the secondary component must calculate intervals for a safe interval for these values in a given situation. Now, how he does it, it should be different from the primary because he wants to have design diversity. But he only calculates these intervals. And it might be that in some cases there are two different sets of intervals. For example, if you go to a stone, to a rock on the road, and you can pass the rock at the left side or pass the rock at the right side, then there would be two solutions to the problem. You either go on the left side or to the left side. So the secondary component would say you can go left side, it's safe, and go to the right side, it's safe, but don't go straight into the rock. Okay? Now, there's another point here which I should mention, that we would like the sensors to observe the environment at the same instant in time. Because if we don't have a clean synchronization here, if every one of these systems looks at the environment at a different point in time, then it might come to completely different conclusions, because the environment changes continuously. So we need a strict synchronization that we get a snapshot of the environment by all sensors at the same instant, and this requires a fault-tolerant clock synchronization. Clear? Yes, Martin.
The question. So, in the case of automated driving, because there is so much uncertainty, it could happen that your diverse components, the primary and secondary, rather often, on a busy road, might not agree.
Well,
They might both be right, but they may not agree.
well, this I just mentioned, it could be that we have two completely different solutions to a given situation. And the secondary component would have to provide both solutions. And the primary component selects one, A or B. But they both must meet the criteria of the envelope given by the secondary component. Okay? Let's go back. So we have covered the independent component for every essential function, normal processing from safety assurance. I'll skip over the last three rather quickly because they are easy. Client actions from server actions. It's a clear separation of functions. A client gives a problem to a server, and the server uses the resources of the server and to provide an answer from the client. So it's a clear separation of concerns. Edge case detection from edge case handling, that's another interesting issue. Because, for example, if you drive on a road, and an edge case is something which happens infrequently but is difficult to handle. For example, if you drive on a road and you have a construction zone and you have bad weather, icy conditions, that's an edge case. It doesn't happen very often, but it does happen. And the idea is that edge case detection, that you detect that something is not part of your normal processing, should be in one component. But the handling of the edge case, that means how you handle such a situation, should be in a separate component. That's already a level below. We are now already doing the level below. Because edge case detection and edge case handling are completely different things to do. And in the primary component, it's sufficient if you can detect the edge case, and then the edge case handling should be done independently in another component. And there may be many different edge cases that you have to consider in a drive-by-wire situation. For example, if the car ahead of you starts burning and there's a fire, or whatever there could be. All these edge cases, they are the difficult, they make the whole thing really complex, all these edge cases. If you drive on an autobahn on a normal situation, it's relatively easy. But if you get all the edge cases involved, for example, if the ambulance comes, or if the fire truck comes and you have to go into sidelines and whatever, these are edge cases. And then control data from archival data. I don't want to go too deep in this, although I could give a separate talk on this such last point. But just the point, control data is time sensitive. And archival data is storage sensitive, if you say. Control data loses its validity as time progresses. And archival data, once it's captured, you should keep it in storage because it's needed for later legal or whatever purposes. And you should try to separate the two as early as possible. So we've handled the horizontal. Now let's go into the segmentation area. The segmentation says we partition in the temporal domain. And we try to partition the problems temporally so that different subsystems handle a problem at a different time. And the first one, the first two actually, they are closely related, is separate the temporal domain from the value domain. They should be completely independent of each other. Let me give you again an example. We had just before this particular system, and now we are going into the next level down in our hierarchy and try to develop a structure for the next level, for the level n-1. And there we say we have different data acquisition subsystems. That means we have radar and LiDAR and cameras or whatever. Then we have sensor fusion. Then we have trajectory calculation, and then we calculate the output. That means, in essence, the next set of acceleration values and brake values, which going back to the decision component. Now, if we partition the time and say this part is taking in one step, then we have communication. Then the second part is taking place. Then again communication. The third function is calculated again, and we develop a temporal control structure as it is done in the time-triggered architecture. Then we have separated value domain from temporal domain, because all temporal concerns are somehow represented by the structure of this graph. And the value, remember yesterday we talked about the modeling relation. And we said that there's an algorithm that calculates out of the inputs, the outputs in a time-independent way, just knowing for what time in the future it must calculate the outputs, if you remember the modeling relation. And this is exactly the case here, that we have given time intervals, we call it the service intervals. We do time-triggered communication. There is no delay, extra delay in the communication, just a minimal delay. Everything is synchronized, and we can come within the given time constraint from this point to this point. And by putting here temporal firewalls between the components and using possibly anytime algorithms, which we discussed yesterday, then we can make sure that the given time is used to the very best way in these components. And we can set up this temporal control structure, as I call it. I mean, I call the temporal structure between the different components here the temporal control structure. And I don't need really much at the early phases of design. I don't need very much. I can do this right at the beginning of design. They say I need the bandwidth of the communication system. I need the duration of the sampling interval. I need the length of the message. And I need the service interval, which is required by the components to do the value calculation. And this is sufficient information to develop this temporal control structure. This is outlined here. And this information of the temporal control structure is then given to the developers, and now everybody can develop his component independently of everybody else. And there's no side effect during integration, because the temporal control structure, the data that's coming in and the data that's coming out is already fixed at a very high level of design. So this again is a very powerful application of the principle divide and conquer. And this is, I think, one of the reasons why time-triggered architectures are so much better than event-triggered architecture, where the temporal and the value domain is always intermixed, and you always have a change in one and the other and so on, and you never can get this clear separation of concerns. Of course, you make first an estimate of these parameters, and then in the second phase, when you understand more and when you've learned more about the algorithms, you can redo the temporal control structure. You can say I needed more time here, less time here, message get longer or shorter. So I changed my temporal parameters, but this will not change the overall architecture of your system. It might only be that it changes the number of iterations in any time algorithm that can be done, and so on. Any question to that here? Well, we're getting along quite nicely. Okay, let's go back. So a temporal domain and value, then different operational modes, I think that's clear if you have an aircraft on the system for an aircraft, and you can have different operational modes like taxiing, takeoff, cruising, landing, taxiing, and there are different operational modes which can be handled by different components at different times, and there's no interaction between them. The big advantage of segmentation over this horizontal partitioning is that if something happens at different times, there cannot be any indirect interaction because one happens at that time, another one happens at another time, and they are separated in time, which is not the case in the horizontal interaction. And then, of course, this is a very well-known technique in batch production system where you do batches, one here, then the next, and the next step. I don't want to go into detail at that level here. So now we come to the next level, the vertical partitioning. Okay, we had horizontal partitioning, we had segmentation, and now we go into vertical partitioning. And in vertical partitioning, we have three different possible alternatives to consider: platform abstraction, abstraction by specification, and abstraction of models. The most important of these is the platform abstraction. I'm sure that you are very well aware of the separation of an application from the platform that provides the execution environment for the application. And for example, in the Android or iPhone, you have the platform given to you by Apple, and then you have the application that use the platform. And I think the idea to separate the applications from a platform is a very powerful idea because many services that are needed by many different applications can be provided by the platform. For example, all this error handling, internet connectivity, machine communication, fault handling, all of this can be done at the platform level. Security can be done at the platform level, which I think is very important. We discussed extensively yesterday, and I think the security should be part of the platform. And then the application doesn't have to be so much concerned about this issue. So separating the platform from the application makes a lot of sense, and I think it's a well-known technique to simplify an architecture. Abstraction by specification is another way. I mean, when you give a specification to a customer, the specification contains all those properties of the system that the customer is interested in. And he leaves everything else free for you to decide. So if I have a good specification, it is not over-specifying. It only focuses on those issues that the customer really needs and leaves all other things unspecified. It means they can be decided at a later implementation level without having an effect on the relationship between customer and implementer, user and implementer. I think we could have again a separate talk on interface, on user interface specification, on specification in general. But this is the guiding idea. Never over-specify. Because if you over-specify, you limit the design space for the implementer. And then if some new things come in, some evolution comes in, all of a sudden the implementer doesn't have any room to integrate the new function because it's over-specified at the other level. So a good specification has a requirements clause, then what are the input data that come into the component, a modifier clause that says what the component is supposed to do in the system and modify the state of the system. What is the output of the component? That's the effect clause, and the temporal clause that says how long does the component need to do this job. So this is at the specification level and sufficient in order to leave freedom to the designer. Now another way of abstraction is abstraction, and I have to speed up a little bit because time is running, is abstraction of models. This again is a very common technique if you have a rather large model and you're only interested in some aspect of the model. For example, you have a large model of a system and you're only interested in safety aspects of the system, then you can take a view of the model and only are concerned with those aspects of the model that have any impact on the safety. This is called the view of the model. It's another way of abstraction of a model to build another model which is simpler. some very short slide here on the relation between static and dynamic structures. I mean, computer scientists like very much dynamic structures. And dynamic structures do in many situations make a lot of sense. But we must realize that dynamic structures are much more difficult to certify and to handle and to get the clarity on than static structures. So you should only use dynamic structure when you really need them. And static structures are easier to reason about. They have a lot lower complexity, objective complexity measure, and they are a lot easier to certify. Now let's go to the next big topic, and that's emergence. And emergence happens, or can happen, in a holonic hierarchy. Remember before we had the holonic hierarchy where the low-level components interact and produce something new at the next level up. And I think emergence is probably the most powerful and the most difficult simplification technique. But it's also, as I said, not easy to do. And I think a lot of the progress of science has depended on the proper identification of emergent properties. I mean, this topic of emergence, let me give you an example in the computer area. If we look at the chip, we can look at it at different levels. At the level of analog circuitry, where we look at voltages and rise times and so on. We abstract from all this and say we're only interested in two stable states, true or false. Then we come to the level of Boolean logic. All of a sudden we have abstracted out of these complicated interactions at the analog level, we abstracted and introduced something new, Boolean logic, which doesn't have to do anything with analog circuitry. But we have a completely new way of reasoning about the behavior by just combining true and false signals in Boolean arithmetic. This is the digital level. And then later on, maybe we go one step further and put bits together to some information chunks, for example, a pointer or a data item or something, and all of a sudden we are at the level of information, of data, and later on of information. So we abstract, so to speak, not only abstraction means that we still have the same kind of property at the lower level, at the higher level, but emergence means that we have a new kind of property. Boolean algebra is not part of analog circuitry, and data science is not part of Boolean logic. So we have exactly new concepts to cover the essential part that we are interested in and forget about the details at the lower level. I mean, if somebody talks about I don't know, a pointer, nobody thinks about the analog values and rising and falling time of resistors at the lower level that are needed to implement this. And we can go further. For example, a message is another abstraction at the higher level, which has a lot of data items in one part. So this is emergence. At the point I would like to say that emergence is our friend and not our enemy. Because many people think emergence is our enemy. No, it's our friend. Because if we have the proper use of emergence, we can really simplify things. But as I said, it's a very, you need deep thinking and a lot of time to find the proper concepts. And let me give you finally, before closing, an example. Look at this structure here. Is it easy to understand what it's doing? And we do a reconceptualization. We say that components 1 to 4 are handling a fault-tolerant clock synchronization. These components are handling sensor fusion, and all of a sudden, this structure to the left here has been represented by this new structure where we have two new concepts, emerging concepts. Out of this one new concept, out of this one new concept, and all of a sudden the things looks a lot differently and much simpler to grasp and to handle. Let me finally come to the conclusion. I think the complexity of a system determines the human effort that is needed for understanding the structure and the behavior of the system, for changing the system, for using the system, for evolving the system. And even a small reduction, if the whole talk which I've given to you results that only 1% of the complexity is reduced, I think it's paid off. Because it's very, very important that we reduce the number of man hours, of women hours, or of time required to understand the system. And even a small reduction is of a significant economic benefits. And the final one probably is the most important one. Cyber-physical systems are artifacts. They are not given to us by nature. We design the systems. And we should design the system such that the human effort to understand the design is really controlled and minimized. Finally, I will give you an ad. I am just in the process of publishing a book which will be published at the end of next month, on July 29 is the date, by Springer Verlag, on Simplicity is Complex. And this book goes in much more detail in what I had to say in the 2 lectures yesterday and today, because you cannot cover a complete book in 2 lectures. Thank you very much.
Thank you very much, Professor Kopitz. Any questions from the audience?
I have a question. As you talked about the time-triggered versus event-triggered systems, how do you deal with that when you have, like, for example, if you stay with automated driving, when you have multiple vehicles and they have to interact somehow? I mean, that's a highly event-triggered system. How do you get that to a time-driven one? Or
Well, that's a very good question, and I also have a good answer, I hope. I mean, what is the difference between an event and a state? An event means a change of state, okay? And so event and states are closely related. For example, if you take an interrupt system on a computer, what is happening that the hardware observes the state of the interrupt line after every instruction, okay? So it's a state-based systems. We have states. But then at the next level up, you are getting an event. You're getting a change of state reported to the software. So there's a close relationship between state of events, and the same is true, of course, in this situation. You observe the environment at certain interval, the sampling times, and then you compare. And if something significant happens, you generate the event you're interested in.
okay.
So you can do it. I have in the book, there's a good example on how to transform an alarm system, which is a very event-based system. Alarm doesn't happen maybe for a year, and when it happens, it has to be processed within a millisecond or so on. And how to transform an alarm system that is strictly event-based into a state-based systems. There's an example in the book. So this is a way to transform it, and you can do it with state-based technology.
Okay, thanks.
Just an observation or a comment rather. So this is a very interesting talk and very thought-provoking. So in my own area, current work of safety cases, they get large and complex, like any other information, artifact. And so you want to try and make them comprehensible to humans, and so many of these techniques are applicable. And so we've introduced the notion of hierarchy, kind of invented the notion of hierarchical safety case. And we wrote a few papers on this, and one reviewer said, why are you coming up with this idea? It's the same as modularity. And I thought, well, it's not really the same. So I tried to think, what is the difference between hierarchy and modularity? And sort of tried to get that clear in my head. And I was Googling around to see if there was literature on these, comparing these topics. And I found very little. And actually, one of the few things I found was Herbert Simon. He sort of talked about these ideas. But I guess your work is very relevant, so I'll have to think more about this.
Yeah. Well, I've thought also a lot about these ideas over the last 40 years. Any further question? Now, this is, I don't know if this is a good or a bad sign. If there's full understanding or no understanding. But I hope that there's some material to digest.
I mean, a reflection, as you mentioned, is that these are the principles, but then you end up in reality with the market and cost drivers, and there's a continuous fight. Because sharing resources, reducing the amount of sensors, sharing is happening everywhere. So I guess that's the challenge in applying. You talked about strong character, right? We need strong architects.
Yes. Well, I mean, the question is, what do you want? I mean, if you want to have really want to make sure by 10 to the minus 9 safety, I mean, take the example of the Boeing 737. I mean, they wanted to make shortcuts in one way or another. And I think it's at the end of the day, it's not a technical decision, it's a management decision. How much are they willing to pay for safety? And I'm just giving you here the view of, I call it a scientist or whatever. And I mean, I'm involved in a company at DTTech, and I know about the daily decisions that come in and say you have to be more economical and you should share the sensors and so on. You can share sensors in some situations, but in other senses, it's a risk you're taking. And the question is, are you willing to take this risk?
But so I guess in many cases, actually monetizing the risk. I mean, in the Boeing case, obviously they were thinking short term, they were not thinking long term, or they were not correctly assessing the cost, because this will cost them much, much more than the proper...
The proper design.
Yes.
Yes. But I think, but that's more the management decision than the technical decision, I
We
think.
need to have more managers coming here.
So actually, I just want to remark that I think that the discussion that you have initiated in this work and in the presentations about simplicity and complexity seems very timely. We've talked about safety and security quite a bit, and complexity is another dimension that maybe can be viewed as a proxy in some ways. It's also kind of interesting to think that in many contexts people view simplicity as a goal. So I think there's a quote attributed to Einstein about making it as simple as possible, but not simple. And if we look at many management books today, Martin mentioned management, simplicity is also very often a theme.